Alkynes part 3. In today's discussion, we shall discuss about the linear polymerization. I'll discuss about the linear polymerization, meaning of the linear polymerization later, as we had discussed some polymerization reactions in the earlier part. So initially, we shall take one particular reaction. Later, I will combine all those reactions to explain the difference between the linear polymerization and normal polymerization. So, in this linear polymerization reaction, we take acetylene molecule. I am taking acetylene. You take two acetylene molecules which undergoes polymerization in the presence of Cu2Cl2 and ammonium chloride. You must be very careful when you see the reagents. So, one of this hydrogen will be shifted here and the pi bond will be shifted here, so that the molecule product becomes CH2, here hydrogen, C triple bond CH. This is called as the vinyl. This particular part is called as vinyl acetylene. This vinyl acetylene, on reaction with one more mole of the acetylene molecule, as well as using the Cu2Cl2 cuprous chloride and ammonium chloride. So now this particular hydrogen will be transferred over here, and this pi bond will be shifted between these two carbon atoms, and finally we get the CH2 double bond CH, single bond C triple bond C, single bond CH double bond CH2. Now if you see here, it looks like that there are two vinyl groups. This is one vinyl part, this is another vinyl part. This is like looking like acetylene, where the hydrogens are replaced by the two vinyl groups. So this is called the divinyl acetylene. Divinyl acetylene molecule. And the same acetylene molecule, if it is passed through the red hot iron or copper tube, approximately at 600 degrees centigrade, as we discussed, there also three acetylene molecules are participating, and we get a benzene molecule. This particular reaction is called as the product is benzene. This particular reaction is called as the trimerization reaction, because three acetylene molecules are participating in this reaction. And even though here three acetylene molecules are participating, we don't call this one as a trimerization reaction, only it is limited to the formation of the benzene. And the same acetylene molecule, again when subjected to the, yesterday we discussed that anhydrous nickel cyanide, then four molecules of acetylene participates in the reaction, and we got this particular molecule which was discussed in the earlier part. If you have any doubt, please open the video and you can check it. So four acetylene molecules are giving this particular molecule, and since four molecules are participating in this polymerization, it is called as tetramerization, since four are participated. And the name of this molecule is cyclooctatetraene. Okay. So now why we know we have to call this particular reaction as a linear polymerization. Linear in the sense straight. So here polymerization reaction, after the polymerization reaction, whatever the molecule you are getting, it looks like a straight like line-like molecule. So it is called as the linear polymerization. But these are not the linear polymerization reactions, where a cyclic ring is being formed. And one more reaction is there, when the same acetylene molecule is subjected with the Cu2Cl2 ammonium chloride. Now use extra thing, that is air. So if air is used, then there will be removal of the hydrogen from this acetylene and hydrogen from over here, this particular carbon. Both of these triple bonded carbons will be connected by a single bond. So molecule becomes like this. So this is the molecule along with hydrogen which will be removed. See, without using the air, using only these two compounds, we are getting the divinyl acetylene. But if you use air, oxidative polymerization reaction takes place. Oxidative in the sense loss of hydrogen is also called as the oxidation. So here what we get is coupling reaction takes place. Coupling reaction means the two molecules, they attach with each other and giving a larger molecule. And similarly, we don't need to use only this particular one. Even you can use example higher alkynes like RC triple bond CH. This particular process is possible only in the case of the compounds having the triple bond CH. Internal alkynes do not participate. So when it is subjected with the two molecules of this one, when reacted with each other in the presence of the Cu2Cl2, ammonium chloride and air. So you must be very careful while seeing the reaction whether air is there or not. So the final product after coupling is plus H2. So this is the molecule what we get actually. Now, other important reaction which is to be learned from here is, if this molecule vinyl acetylene, this is called as vinyl acetylene. So when vinyl acetylene is subjected to the palladium, barium sulfate, acetic acid plus quinoline and heat it. We know that this reagent is called as the Lindlar's catalyst. So what is the use of Lindlar's catalyst? Lindlar's catalyst do not affect the double bond, but it preferentially attacks over the triple bond. It reduces only the triple bond, not the double bond. So that the final molecule what we are going to get is CH2 double bond, CH single bond, CH double bond, CH2. Here I am not saying which is whether it is cis or trans. Actually we get cis, since carbon is having the same hydrogen atom. So we cannot say which is cis, which are trans exactly, because cis and trans is possible if the double bonded carbon atom is having the two different groups. So the name of this particular molecule is but 1,3 diene or else 1,3-butadiene. Okay. So this is one important reaction where to convert the alkynes to the higher conjugated alkenes. Now let's try to learn one more important reaction, that is addition of arsenic chloride AsCl3. Addition of arsenic chloride. So here we take alkyne acetylene. On reaction with this AsCl3 arsenic chloride, I would like to write like this: chlorine AsCl2. So what happens? This undergoes addition reaction, it breaks one of this pi bond and chlorine will be added one side, AsCl2 part will be added in the other side. So we get the CHCl double bond CH AsCl2. The name of this molecule is, here you can see, give numbering from here, this carbon atom first, this will get the second numbering. At second position 1 chlorine atom is there. So we write it as a 2-chloro, and here these two chlorines are not attached to the carbon but attached to the arsenic. That's why I did not count these two chlorines while writing here. So it's a 2 chloro. Next one is 2 chlorines are here. Okay. So 2 chloro, and this particular part looks like vinyl part. So 2 chloro vinyl and 2 chlorines with arsine. It is called as the dichloroarsine, which is very important product, which is called as the levisite. Levisite, which is a poisonous compound which was used in the Second World War. So it is a highly poisonous compound. So to counter this poisonous compound, to neutralize this compound, British scientists, they invented one more compound, that is CH2 SH CH SH CH2 OH. The name of this compound is British anti-levisite, popularly known as BAL, British anti-levisite, which is the counter product for this particular levisite. So these are the reactions to be remembered, and some other addition reactions and oxidation reactions now we shall discuss, which are useful only in the mechanisms. Generally these reactions will not be asked. So other reactions. So in the case of other reactions, first of all, let us take any terminal alkyne. Terminal alkyne means having the triple bond CH. See, here we will take the CH triple bond CH, and they may ask the compound what happens if acetylene reacts with the formaldehyde in the presence of the CH3ONA. Alkoxide must be there. Not only sodium methoxide, even you can use the RONA, sodium alkoxide. Okay. So when it is used, initially what happens, the sodium alkoxide reacts with the acetylene, and it converts this acetylene into the CH triple bond C minus Na plus. So what did we get here? We got the carbon ion. Okay, this carbon ion, now you can see which is a nucleophile. Okay, and here the carbonyl compound, here carbon gets the partial positive charge, oxygen gets the partial negative charge due to difference in their electronegativity. So as a result, this negative charge can easily attack over this positive charged carbon and shift this pi bond electrons. So you must be very careful while observing the reactions and the reagents. They are like a conversion reactions. And this reaction is possible only when terminal alkynes or triple bond CH is there. Then only carbon ion can be created. Once carbon ion is created, that will attack over the aldehyde or ketone, whatever they give. So we get the CH triple bond C. Here O minus will be there, no? So it will be O minus. Okay. Next, this is equals to CH2. So this particular ion we get, and afterwards, on the addition of the H plus ion, because H plus ion is removed here initially, so that will give CH triple bond C CH2 OH. This is called as 1, 2, 3 prop 2 ion 1 ol. Okay, and this reaction we cannot stop at this stage because here still one more triple bond CH is there. So if they say only 1 mole of this, both of these compounds are involving, then we can stop the reaction at this stage. But if 2 moles, or if they don't mention 1 mole or anything, then you need to continue the reaction. So again here C minus will be created, that will attack over the another formaldehyde. So this side also will get the one more CH2OH. So CH2OH, C triple bond C, CH2OH. So this particular molecule get and give the numbering 1, 2, 3, 4. So but 2 ion, and comma should not be used. and here 1 and 4, 1 comma 4 diol. This is the molecule what actually we get. Now let's try to use another molecule. Second reaction, some other reactions we are discussing. CH3 C triple bond CH plus, let us take acetaldehyde CH3 C double bond OH in the presence of the some sodium ethoxide, whatever, alkoxide. We want the sodium part. So here negative charge will be created after the reaction of this one. You should not write the negative charge with hydrogen. Just I am thinking that this is already reacted with the sodium ethoxide and formed the negative part. So this negative part will attack over the carbonyl compound and replaces the pi bond to sigma bond, so that we get the directly molecule I am writing C triple bond C CH2 OH, and after this you cannot carry out the reaction as there is no other terminal triple bonded carbon. Okay, did I write okay? CH3 C triple bond C minus, okay, sorry, I did not write it completely. So this is CH OH, and afterwards this CH3 is there. So this CH3, and afterwards we cannot carry out the reaction. Now let us take the same type of the similar reaction but with the ketone. So in this particular case, C triple bond CLi I am taking. You must remember that here triple bonded carbon with any metal will have the negative charge on the carbon. So not necessarily only sodium. So they may give the compound directly like this only. So in this case, you just take the acetone molecule. Acetone. So here it attacks, shifts like this. CH3, C triple bond C, carbon. Here we will get the OH, CH3 and one more CH3 like this. So these are the some products. Now let us see another important reaction, that is oxidation reaction. Oxidation with the two compounds. One is alkaline KMnO4, second one is acidified KMnO4. So first one is cold dilute alkaline KMnO4. We know that this reagent is called as the Bayer's reagent. Okay. So what happens, this Bayer's reagent on reaction with alkynes, it converts them into the carboxylic acids. You see here CH triple bond CH. I am just writing the dilute alkaline KMnO4. No need to mention the oxygen. It means that already it is undergoing the oxidation reaction. So we get the COOH, triple bonded carbon with hydrogen will be converted to the COOH, means like this, triple bonded carbon with hydrogen will be converted to the COOH, and only triple bonded carbon will be converted to the C double bond O, because it cannot break this particular bond, because it is dilute one. So let us take another molecule, CH3 C triple bond CH, and use the cold dilute alkaline KMnO4. This temperature you should not exceed nearly 30 degrees centigrade. So here we get the CH3 C triple bond O COOH. This is the molecule, and usually this molecules again undergo oxidation and breaks this bond. This COOH will be converted to the carbon dioxide if you further heat it, so that we get the COOH plus CO2. But if you use the acidified KMnO4, H plus KMnO4, then it converts triple bond CH to the directly COOH, and this triple bond RC triple bond to the COOH part. Let us see those two reactions also now. So oxidation with acidified KMnO4. So acidified KMnO4. The property of this acidified KMnO4 is it converts triple bond CH2 CO2 and RC triple bond part, wherever this part is there, to COOH. Means it breaks the triple bond basically. Okay. So I'll take first initially CH triple bond CH. You take H plus KMnO4. So H plus KMnO4, that too at high temperature, means 100 to 110 degrees centigrade. If 30 degrees centigrade means same procedure again. If high temperature means this particular complete breakage of the triple bond. So here you will get the initially this complete bonds will be broken to the formic acid, HCOOH plus HCOOH, and these two HCOOH molecules finally will be converted to the carbon dioxide. But if you take a molecule like this, H plus KMnO4, so we get the RCOOH plus HCOOH, formic acid, basically formic acid. If you use the high temperatures, then this formic acid again will be converted to the carbon dioxide. Now let us take the CH3, C triple bond C, CH3. So heat it. So we will get the two molecules of CH3, COOH. This will be broken, this will be COOH, and this also will become the COOH. Now, let us take the same molecule, means I'm going to take the different reaction with high temperature and lower temperature. I'm going to write down the two reactions here. This molecule I'll take. So here CH3, C triple bond C, CH3. You just take two reactions. So H plus KMnO4, they said at 100 to 110 degrees centigrade, and simply KMnO4 at 30 degrees centigrade. So the products over here are CH3 COOH plus CH3 COOH, means two molecules, completely breaking of the triple bond will be there. But in this case, so it will be converted to the CH3 C double bond O, C double bond O, CH3. So this is the molecule if you use the 30 degrees centigrade. Okay. And let us take another molecule, CH3 CH2 C triple bond CH. H plus KMnO4, 100 to 110 degrees centigrade, and KMnO4, 25 to 30 degrees centigrade. Then what must be the products if you use the higher temperature? It becomes the CO2 and this becomes the COOH. So we get the CH3, CH2, COOH plus CO2. And in this case, this becomes the CO part and this becomes the COOH part. So we get the CH3, CH2, C double bond O, COOH. So these are the molecules. And let us see another very important reaction, and usually people neglect this reaction, that is oxidation with selenium oxide. Selenium dioxide. So in the case of the oxidation with the selenium dioxide, the important thing is triple bonded carbon will be converted to the carbonyl compound, SeO2 oxidation. So this becomes carbonyl compound, this becomes carbonyl compound without breaking of all the bonds. Only 2 pi bonds will be broken. So carbonyl compounds means CHO, here also CHO. Now let us take the propyne molecule CH3, C triple bond CH. Use the selenium dioxide. This is a very important reaction. Just you see, triple bond CH will be converted to the CHO, and this triple bond C with alkyl group will be converted to the keto. So here we convert this one into the C double bond O, CHO. You can see now aldehyde as well as the keto groups both are present in the same molecule. It is called the 2-keto-propanol aldehyde. And if you use the KMnO4 at lower temperature, keto group as well as the carboxylic acid, both will be produced. If you don't want carboxylic acid and we want only aldehyde, then we can use the SeO2, selenium dioxide, as the oxidizing agent. Now, the last reaction and important reaction of this category is oxidation with diborane. This is also called as the oxidative hydroboration. Oxidative hydroboration. So the interest and important thing in this reaction is, you just take the terminal alkyne. I am discussing about the terminal alkynes. Even because I am not writing the things over here, just I am explaining because you have the facility to watch the video once again. So terminal alkynes on reaction with the BH3 in the presence of the tetrahydrofuran. So whenever BH3 are using, you need to use the 3 alkyne molecules or 3 alkene molecules. So we get the CH3, CH double bond, CH single bond, taken thrice, boron. This on reaction with the H2O2 in the presence of OH minus, and we get the 3 molecules of CH3, CH double bond, CHOH. But the molecule having double bonded carbon having the OH is unstable, so that immediately undergoes tautomerism and finally gives 3 CH3. Here this is CH2, CHO. So which molecule we got here? Aldehyde molecule. So terminal alkynes are giving the aldehyde molecule. It is impossible to get the aldehyde molecule from terminal alkynes in the normal hydrolysis reaction. I will write down that reaction also. So I will select the another color pen. You just take here, yesterday we discussed mercuric sulfate, 1% of mercuric sulfate and 40% of the sulfuric acid and H2O water. So H plus and OH, hydrogen will be added here and OH will be added over here. So we get the CH3, COH, double bond CH2, which undergoes again tautomerism, so that we get the CH3, C double bond O, CH3. Normal hydrolysis or hydration reaction of the terminal alkynes. I am not discussing about the internal alkynes. Anyhow, internal alkynes, whether you follow this method or this method, you get the ketones. But the terminal alkynes with hydroboration gives the aldehyde as the compound, whereas with the normal hydrolysis reaction they give the ketones as the compounds. Even if you use the another internal alkyne, say the compound is this one, CH3, C triple bond, C, and say CH3. Let us take both the reactions. BH3, PHF, this is the first step, and the second step is H2O2, OH minus. Any steps you use here, you will get the CH3, C double bond O, CH2, CH3 ketone. And in this case, use the 1% HgSO4, 40% H2SO4 and water, also you get the same product, CH3, C double bond O, CH2, CH3. Means internal alkynes means triple bond is not at the end position. So internal alkynes on hydrolysis with any of these reagents use the ketones as the major products. But terminal alkynes gives different products. With oxidative hydroboration they give the aldehyde, and normal hydrolysis they give the ketones. So today's reactions are so unique and important reactions because small difference in the change of the reagent will change the product itself. So that's why you remember normal reactions you can remember, but this type of the reactions becomes difficult to remember. Hence I request you, please do remember this type of the reactions. Now, separation of alkynes, alkenes and alkynes. So I'll write down here heading distinction. Distinction in the sense identification. How to distinguish? Distinction of alkanes. I am taking here methane or ethane. I'll take ethane. 2 carbon molecule. C2H6. Alkene. So for alkene I am taking ethylene, C2H4. Alkyne, I am going to take the C2H2, that is acetylene. So you must remember that this is acetylene, means terminal alkane, not the internal alkyne. So I'll write down those compounds initially. So here first of all it is the property of the compound. You first remember and note down this one, property. And here ethane, ethane in the sense alkane, ethene, alkene, ethine, alkyne. So how to distinguish these compounds? First one is molecular formula. What is the molecular formula? Physical distinction is different. This is only by formula. CN H2N plus 2. Here CN H2N. Here CN H2N minus 2, alkynes. Second one is nature. So this is saturated, this is unsaturated with a double bond between the carbons. This is also unsaturated, a triple bond between the carbons. These are general distinguishes. But now let us see on chemical distinguishing how to identify these molecules. So I am going to write down important reactions from here, from third onwards. Reaction with H2. Saturated compounds do not react, and these alkenes reacts with, means I will write directly, anyhow I am explaining now, reacts with 1 mole of H2 and gives alkanes. And this one, 1 mole of H2, if you use only 1 mole of H2, so 1 mole of H2 if you use, we get the alkene, and if you use the 2 moles of H2, we get the alkene. So how can we distinguish these compounds? Initially these compounds, alkenes, do not react, but alkenes react with 1 mole of H2. Alkynes react with the 2 moles of H2 to produce the alkane molecules. And fourth reaction is reaction with concentrated H2SO4, that means hydrolysis. Alkanes do not react, but these molecules, whatever the alkanes are there, they react with the concentrated hydrogen sulfate, means I am taking the directly ethylene molecule subject with the H2SO4 in the presence of the H2O, so you will get the ethyl alcohol. Alcohol is the product, but in this case you will get the, means ethane molecule I have taken, so that CH triple bond CH On reaction with the H2O in the presence of the acid catalyst, we get the CH3CH2O aldehyde as the product. But with the help of these reactions, we cannot physically identify. These are only chemical identification reactions. Then how to identify these alkynes, alkenes and alkynes physically? Physically means just by seeing the reactions itself, you must be able to identify it. So for that purpose, we use the bromine chlorine, carbon tetrachloride, CCl4. So it is a reddish brown colored liquid. Alkenes do not react. Alkenes decolorizes. And alkynes also decolorizes. I am not writing the products because products have been written already. So both of these compounds decolorizes bromine CCl4 liquid so that alkanes can be separated from unsaturated compounds. So this reaction is helpful in identifying only unsaturation. And cold dilute alkaline KMnO4. This is Bayer's reagent. So Bayer's reagent, alkanes would not react, but alkenes and alkanes react. We have written they decolorizes directly. Means if you want the reaction, I'll write decolorizes and decolorizes. So with the help of these two reagents, we can separate only alkanes from these two compounds, but these two compounds cannot be separated directly. If you want the reaction for this CH double bond CH2, anyhow it was discussed already. Here you write down the Bayer's reagent. So you will get this CH2OH and here CH2OH glycol you will get. But in this case CH triple bond CH, Bayer's reagent, you will get the formic acid, oxalic acid. Okay. Then how to distinguish these two compounds from each other? How to separate them? Then we need the help of another different reagent, that is, we know that ammonical cuprous chloride, Cu2Cl2. Alkanes do not react, alkenes do not react, alkynes, the two terminal alkynes react and they form the red PPT. Reaction has been discussed in the regular classes. So 8th one, Tollens reagent. So alkanes do not react, but terminal alkynes react and they form the white PPT. So if you take the internal alkane, they also don't react. So first of all, you have to separate the alkenes and alkynes using this type of the reaction. Then you go for the terminal alkane or internal alkane. Dear students, hope you understand my explanation. If you understand, share the video, like, comment the video and subscribe the Classroom Point channel. And in searching the Classroom Point in YouTube, you must type Classroom Point continuously without giving gap so that you can find my channel. Thank you.